In this set of videos, we are going to look at the design goals that we have when we are trying to create a register based interface for interacting with a hardware module. So, we will talk a bit about a few of these topics. First would be about how we can construct clean byte maskable register banks and interface them with the AXI Lite bus interface. Common behaviors that we would like to see with the registers that we are using and why we want those kind of behaviors. For example, read write, read only, write one to clear, self clearing pulses and so on, right. We will also bring in the concept of what are called shadow registers, which are useful when we want to update the behavior of a piece of hardware, but we also want to make sure that it does not disrupt what is currently happening inside the hardware. And all of this will be coupled with a demonstration of a piece of RTL code written in Verilog, which we will first walk through the code and then simulate it using Cocotb to see how it works. So, the first question is, why would we want to use register banks? What is their purpose when we are trying to design custom hardware of our own? So, we have already discussed the idea of how we would like to have hardware blocks and we would like to be able to control them using a memory mapped IO interface. Now, what exactly do we mean by control? Typically, it would mean some kind of parameters of the hardware that we want to set or to query. We want to see what the current values are and if necessary to change them. This allows us to create a small and easily discoverable API. So, what is an API? It stands for Application Programming Interface. It is more common to hear the term API used in the context of pure software development, but of course, embedded software is also a form of software. And an application programming interface essentially provides you with a set of functions that allows you to change the behavior of a piece of code or hardware or something, whatever it is that has been created, in a way that does not involve knowing the details of how the hardware was implemented. So, in the context of, let us say, a function for performing linear algebra, your API might consist of a set of calls perhaps for performing matrix multiplication, matrix inversion and so on, and you do not need to know how exactly the matrix multiplication was implemented. Was it using for loops, was it using vectorized instructions or some other approach. In our context, in hardware, we have certain kinds of parameters of a piece of hardware that we are designing and we would like to be able to adjust those. So, what we do is we provide an API, in other words a set of function calls that allow people to directly either change a parameter or to check the value of a parameter. Now, what we mean by a discoverable API is that by just documenting the set of registers that we have and by documenting what are all the side effects of writing to particular registers or of reading from particular registers, we can provide a very simple API that can be understood by anyone who is intending to write embedded software for this system. It also allows us to decouple the timing of the data path, the speed at which the data path works, the number of cycles that it needs and so on, from software transactions. In other words, we can have some kind of flag based querying mechanism where we would be able to check whether a particular operation has completed and then move on to the next stage, or even better, one of the registers might actually allow us to work as some kind of an interrupt mechanism and we can either enable or disable interrupts and so on. This also enables a significant amount of debuggability and observability because we can insert status bits, counters, we can keep track of how many events of various kinds have happened inside the system and make them in such a way that from the software interface we can query those values and if necessary print them out or do something with them. So, in other words, let us say for example, you have a network interface, it is very easy to expose a particular register which basically says this is the number of packets that have been received by this network interface from the time that the system was started. So, things of that sort can be very useful in practice. Now, typically this information about the register banks is provided as part of the data sheet corresponding to any piece of hardware. Now, the data sheet typically has two portions to it. One is the so called functional description, which basically says what does this hardware do, what are its limitations, when would you want to use it and so on. And then you have what is called the programmer's model, and the programmer's model deals with the question of how should you use it, right. The difference of course being that first you need to understand whether this is the right model for you. So, the functional description allows you to say, okay, what does it do? Does it solve the problem that you are interested in? And then of course, once you have decided that this is the right thing to do, you need to figure out how to use it. And the programmer's model with all the register interfaces and various other information that is necessary for writing code to interact with the hardware, that will combine to give you the programming interface. Now, as an example of this, I am going to use this UART, the Universal Asynchronous Receiver Transmitter, which is developed by ARM, and we will shortly be looking at portions of the data sheet of this peripheral, right. It is something which is used inside ARM processors. Once again, this picture is from the ARM website, right, and I will be talking a little bit more about it, but for now I just want to sort of draw your attention to a couple of things. One is there are a whole lot of input and output interfaces, interface pins associated with a device like this. You might think that a UART is actually a very simple device. After all, it is essentially supposed to be a 2-pin, right, just one transmit, one receive, and on the other side there is a FIFO buffer. But as you can see over here, there is a reset, there is a clock, there is another reset which is perhaps for the peripherals. There are a bunch of select, enable, etc. signals. There is also something that allows you to write into this, and the data. All of this essentially provides some kind of a bus-like interface. There are a bunch of other things that you can see over here which are related to what is called the direct memory access or the DMA interface. Now, as you can imagine, DMA is primarily used in scenarios where you want high throughput, a large number of bytes in a relatively short amount of time. So, programming it is not trivial, but on the other hand is fairly it is well known. So, there is a systematic approach to do it, but you need various kinds of things such as the DMA request, the address requests, and so on, and all of those are essentially provided by the DMA interface. There is also another block out here which takes care of the FIFO being a kind of buffer that allows you to, let us say you want to write data out of the UART, you just, rather than waiting for each individual byte to be sent out, you can just fill in a set of values in a FIFO buffer, first in first out buffer, and the hardware internally will take care of serializing it, picking it out one byte at a time and actually sending it out, and it will take care of all the handshaking and other things that are required to send it. So, as you can see, even a simple block like a UART, the actual hardware interface over here, for example, consists of a baud rate generator which actually allows you to get to the serial speed that you want. There is a block called a transmitter and receiver, each of which would be looking for things like the start signal, the timing of the bits, the stop signal, and the parity checks. There are two FIFO buffers. So, all of this part, in other words, consists of the actual hardware that you would associate with a UART. This entire block out here is the bus interface. In this case, it is called the APB interface, which is essentially, APB was the earlier form of the AXI interface, essentially the same thing, just with slightly different terminology. There is a DMA interface, once again for high speed, large amounts of data to be transferred, and the FIFO interface, which is used for things like how to generate interrupts, how to check the status of the FIFO, and so on. So, if you look carefully, you will notice that the number of interface signals that are related to the control and management of the UART is much higher than the actual signals that are required for the UART to operate, okay, which is not uncommon. You could typically have quite a few devices where perhaps this entire module that you are creating may not even have some kind of communication with the outside world. It might just be some computation that is performing internally, but the rest of the interface that it needs in order to communicate with the CPU could by itself start to get a little complicated. Now, what do we do with this? In other words, if we read through this part and look carefully at this picture, we will understand the what. What is this device capable of, right? And the functional overview will describe a lot more in detail. For example, what kind of baud rates can be handled, what is the depth of the FIFO, and what is the implication of that in terms of how the data can be sent. Any information that you really need to know as far as the transmitter and receiver are concerned. For the most part, from the software point of view, you probably do not even need to know how these work, right. The rest of it is sort of a black box. It is the interface circuitry which provides you with a standardized programming interface, which takes us to the next part, which is basically the programmer's model, right. And this programmer's model is a list of registers and also different usage scenarios. How should you use different registers and what should you set or read from different registers at different points in time. Now, one of the things that you will notice when you look through this data sheet is that the base address is actually generally not fixed, not just generally. In pretty much any modern peripheral based system, you will find that the base address of the device that you are trying to create is not fixed. What exactly does that mean? We will get to in a moment when we look at the address space corresponding to a UART. What is done instead is that each register that you have for the UART is given an offset within the address space, and the offsets are fixed. They are part of the data sheet and you need to follow this if you want to communicate with the peripheral. You will also find that there are a lot of locations that are marked as reserved or unused, and the idea is that these are subject to change. In general, when you are trying to interface with the interface your software with the hardware peripheral, you should not make any assumptions on what data you will get if you read from one of these unknown locations, or what will happen if you write to one of the unknown locations. They should not be used, they should not even be accessed, because as we will see, even just trying to read from an address can sometimes have strange side effects.